Hey everyone, and welcome to today's Explainer. If you've been following the AI news space lately, or really, if you've ever tried working with these systems, you know that getting a generative model to do exactly what you want is, well, it's tough. It often feels like wrestling this massive, computationally expensive beast. But today, we're looking at what is genuinely a paradigm shift in how we steer flow matching models. It's a brand new method called reward transport. It was just detailed in a recent paper alongside an open source release, and it is a real game changer. So let's dive right in.
Think about this for a second. What if controlling generative AI cost absolutely nothing when you actually run it at inference? Right now, we are paying a massive computational tax just to steer these models. It's kind of like buying a high-performance sports car, but then having to pay a mechanic to sit in the passenger seat and physically yank the steering wheel for you every time you want to take a corner. We build these incredibly powerful models, and then we have to bolt on all these extra guidance systems, reward models, and complex math during the sampling phase just to get the outputs we want. But what if we could just kick that passenger out entirely? What if we could eliminate that inference time tax completely?
Here's our roadmap for today. We'll start with the generation control problem, then introduce reward transport, look at how noise space alignment actually works, dive into some proof using molecular generation, and finally, wrap up with a developer guide.
All right, Section 1, the generation control problem.
Currently, standard flow matching pipelines are kind of a headache. To control generation, let's say making sure a model outputs a molecule with a very specific property, you usually have to rely on explicit conditioning or some form of post-hoc guidance. Practically speaking, this means you are constantly computing gradients during sampling, dealing with really high latency, and maintaining completely separate external reward or oracle models. It's clunky, for sure. But reward transport promises a totally different approach. No oracle, absolutely no gradient-based sampling adjustments, and zero extra cost at inference. It basically takes the entire burden of control and shifts it completely upstream.
Which brings us to Section 2, introducing reward transport.
Okay, so what's the secret sauce? It comes down to a concept called optimal transport coupling. Now, in standard flow matching, pairing noise vectors with data points during training is usually just treated as, a purely computational choice to make the training a bit easier. They pair them up independently, which means the noise itself doesn't actually carry any property structure. But reward transport flips this completely on its head. It uses this coupling as an alignment interface. It basically embeds the controllable structure directly into the learned flow field while it's training.
I absolutely love this quote from the source material because it really captures the aha moment of this whole research. They write, "The coupling defines how noise vectors pair with data points. This coupling can instead serve as an alignment interface." So what used to just be a mathematical chore running in the background is now this incredibly powerful tool for alignment. The flow field natively internalizes the relationship between the noise space coordinates and whatever target properties you're after. And the most crucial point here? Zero. Because all that alignment is baked directly into the coupling matrix during training, the computational cost to steer the model later at inference is exactly zero. You don't need an external oracle, you don't need a bulky reward model, and you don't need gradient guidance. Sampling just proceeds at your standard, super fast flow matching speeds.
Moving right along to Section 3, let's look at how this noise space alignment actually works under the hood.
You might expect the math here to be a total nightmare, but it turns out to be remarkably simple in practice. Think of it as a three-step matchmaking process. Step 1, you sort your noise by magnitude, specifically its L2 norm. Step 2, you sort your training data by whatever target property you want to control, like say a molecular property such as log P. And step 3, you just pair them up, rank by rank. That right there is the unique 1D optimal transport plan under any convex cost. You are literally just taking the biggest noise vectors and lining them up with the highest property values. It's brilliant.
And because you did all that rank-by-rank matchmaking during training, the interface you get at inference is incredibly elegant. It all boils down to a single noise space scalar that acts as a continuous dial. Developers can just sweep this one single value to smoothly traverse the reward landscape. You aren't fighting with discrete conditions or dealing with the instability of classifier-free scaling. You literally just turn the dial to steer the generated distribution exactly where you need it to go.
Now, they aren't just hoping this works. There's a rock-solid structural guarantee here. In what the researchers call the coupling-preserving limit, thresholding this scalar mathematically recovers the exact truncated reward distribution you would get from a step of the cross-entropy method. So this bridges this super smooth distribution-level control knob with deeply established optimization techniques. It's a mathematically grounded feature, and you get it all in a single forward pass.
Okay, Section 4. Let's look at some real-world proof from molecular generation.
The researchers put this to the test on drug discovery datasets, specifically zinc-250K and guacamole. They use the exact same single scalar knob to control two entirely different target properties, log-P and QED. But look at the structural response here. When they turn the dial up for log-P, the generated molecules physically grow in size. But when they turn that exact same dial up for QED, the molecules physically shrink.
And this is absolutely crucial because it brilliantly illustrates why the method is so robust. These opposite structural responses are the definitive proof that the model isn't just, cheating. If the molecules always just got bigger, you might think the model just had a generic size bias, or maybe it was some weird latent capacity artifact. But because the response is the literal opposite depending on the specific property it was trained on, we know for a fact that the control is genuinely and definitively property-specific.
And the precision they achieved is just stunning. When sweeping this scalar for both log-P and QED across its operational range, the method hit a perfect monotone correlation score, a row of 1.00, and it did that while maintaining 100% validity. The training objective successfully regularizes the coupling, completely preventing reward saturation or mode collapse.
Let's get practical with Section 5, the Developer Guide and Implementation.
If you want to integrate this, here is your step-by-step checklist. First, you can go clone the open source repository right now. It's at keyhandguo/reward transport. Second, take a look at the coupling implementation. The core mechanism is surprisingly lightweight. It's only about 50 lines of code in a file called iot/coupling.py. Third, integrate this optimal transport coupling right into your training loop against your target scalar. Fourth, when you start sampling, make sure to validate your operating ranges so you can monitor for any saturation outside the training distribution. And finally, benchmark the whole thing against your current classifier-free guidance baselines using your standard metrics. Actually, wait, before you dive in, I do need to point out one structural limitation noted by the authors. If your current pipeline strictly relies on epsilon prediction diffusion, this specific coupling level alignment is structurally absent there. So that kind of delineates the boundary of where this method works today. You would need to switch over to a flow matching compatible formulation to actually take advantage of this zero-cost control interface. So we've seen how reward transport takes the massive, complex burden of generation control and just elegantly shifts it upstream to the training phase through optimal transport coupling. No extra models, no latency, just a single continuous dial at inference. It's wild. So I'll leave you with this provocative thought. How will you rethink your training loops and deployment architectures now that inference control can be handled entirely upstream for free? Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.